Today, let's look at the system design for distributed job scheduler. So the problem statement goes like this. Create a distributed job scheduling system that allows customers to submit jobs, view the status of their submitted jobs, and query the output of the scheduled jobs. The system should be designed to efficiently manage job submissions, scheduling, and the resource allocation across a distributed environment. Before discussing further, let's remind ourselves of the design discussion framework. First, we should have a very good understanding of the problem statement. Then we should list down the requirements, and that might include some back of the envelope calculations, some design tenets, talk about system correctness requirements, operational requirements, and also clearly lay out what is in scope and what is out of the scope. Then we should put a high-level design, which might include some APIs, schema, interface, and then based on that, we can go into low-level designs and discuss dependencies. After that, it's good to discuss failure modes of your system design. And then if time permits, we can talk more about operational readiness requirements like observability, experiments, security, and durability aspects of your design. So for distributed job scheduler, here are some of the clarifying questions that we may ask. How many jobs per day? So let's say it's 1 billion jobs. The second question could be, what's the nature of these jobs? What is the average runtime of these jobs? So let's say the operations could be between 5 minutes to 5 days. And then are we giving some guarantee to customers on the job ordering? And let's go with no. Now let's look at the requirements for the distributed job scheduler. So some of the functional requirements could be, users should be able to schedule jobs, query status of their jobs, and get notified when the job has reached a terminal state. A terminal state could be defined by finished, aborted, or failed. Now some of the key non-functional requirements would be a good isolation between customers and jobs. That is, we should aim to provide a single tenant experience. The system overall should be fair. That means we should avoid noisy neighbor problems, and job and a customer shouldn't starve. Job should reach a terminal state, which could be finished, aborted, and failed. We should guarantee at least once job execution. The system overall should scale horizontally with number of jobs and customers. And in terms of data durability, job-related data, metadata, and output should not get corrupted. So given these requirements, I think we are ready to put a high-level design and then discuss further. Now, let's do some napkin math before putting a high-level design. So in terms of overall storage, we assume that it's 1 billion jobs per day. That means 10,000 jobs per second. And that means assuming 1 kilobyte of metadata per job, we have 1 terabyte of storage per day. That means 30 terabytes per month, 360 terabytes per year, and around 2 petabytes in 5 years. And in terms of network bandwidth, that would mean around 80 megabits per second. Also, what is not in scope? So let's say users can't cancel the jobs once they have submitted. There are no job order guarantees, and metering and billing is not in scope. Here's the high-level design for distributed job scheduler. So the story starts with user, as it should. So user creates a new job and submits. It lands on front-end fleet, which has load balancer and bunch of web servers. Web servers talk to job metadata service, which has metadata store. So it extracts all the metadata and stores in the metadata store, which can be DynamoDB table. So as part of this process, we also create mutation events. So those mutation events are published to job events queue, which can be a Kafka queue. In this case, it will be a new job creation events, and those events are consumed by job scheduler service. The job scheduler service then, its key responsibility is to just schedule jobs. So it creates a bunch of workers for that job, and it schedules. So the workers take the job and work on it. And their responsibility is to publish reports as the job is kind of progressing and transitioning state. Let's say from new, it will transition to in progress, and then it will transition to a terminal state, which could be completed, failed, or aborted. And at regular intervals, it also publishes heartbeat to job report and heartbeat service. And job report and heartbeat service talks to metadata store, where it stores all these train transitions and also heartbeat signals. Now, in this high-level design, there are two other boxes I've not talked about. One is job redriver. So let's say the job fails and we want to retry. So there are multiple ways we can do that. One of the way would be to again reset the state of the job as new, mark it as retry number 1, and publish that event to job event queue, and then the rest of the flow will follow. The other approach could be we can have a separate queue for retry, and ultimately, we have exhausted the number of retries. We can mark it as kind of completely failed and put that in a dead letter queue. The other box is job notifications. So let's say user has signed up for, they want to be notified whenever the job transitions one state from another. So we can actually capture, consume all the events, all the mutation events from job events, and the job notification service can publish those events to user. So this completes the high-level design. Let's now look at the key APIs and interface. So here are some of the key APIs and interface. So between client and front-end fleet, when a user creates job, the request parameters will have client ID, job config, its version, blob ID, priority, idempotency token, and some timestamps like expiration timestamp and a checksum. Checksum we are including for the data integrity. And as part of response, we'll respond with tracking job ID, timestamp, and the version, and the checksum. Now, here is report job completion interface. So here we will have request checksum, request schema version, completions as part of completion. Metadata will have tracking ID, checksum, schema version, execution status, result, payload, and timestamps. The heartbeat request schema will have request schema version, checksum, and as part of heartbeat, we'll be tracking task ID and heartbeat expiration time. Now, as part of notification interface, some of the key parameters would be the report payload, which will have task ID or job ID, tracking ID, execution status, termination timestamp, notification token, result payload, and errors, specifically scheduling errors, which will have error code and message. Apart from this, we'll also have checksum and schema version. Now, let's talk about job fairness. Job fairness is an important aspect of the system. So we can structure this by operation type. Let's say one of the job operation type is tagging. We want to tag a bunch of objects. Now, for that operation, we can round robin between users. Let's say user 1, user 2, user 3. And for user 1, we can round robin between priorities. So we won't round robin between priorities, but for a given priorities, let's say P1 in this case, we'll round robin between tasks. So first we'll complete task 1, task 2, task 3, task 4, and so forth and so on. And then we'll go to P2 and then P3. Similarly for user 2 and user 3. Let's talk about some of the key subsystems of this overall design. So first is job metadata service. It stores job-related information. It exposes APIs to query job-related information, and the queries could be related to job state. The users might be curious about job completion, failures, aborts, or expirations. The storage here is, it could be relational store or key value store. Both could work. Some of the key attributes of that storage system would be it should be low latency. So for example, DynamoDB fits the bill here. And then we can also have a cache on top of the storage, where we could kind of, cache the active jobs. Then there is job scheduler service, which schedules jobs for execution by customer-specific clusters. So its key responsibilities would be to spin up a cluster for the job. We could leverage Spark instances. We could also purge the cluster upon completion of the job, which we should for cost reasons and efficiency reasons. It honors priority and it updates the job metadata service with the customer job cluster info, and it talks to report service to update the status of the job. Coming back to workers. We have discussed this before. So workers heartbeat to job report service, and they are part of auto-scaling group, which auto-scales based on load signals like CPU and memory. In terms of observability, we should track performance metrics and availability metrics for the system. Some of the key metrics would be number of jobs submitted by users, API stats, end-to-end job runtimes, number of jobs that are read-driven, state transition latencies, job terminal states, for example, the number of jobs in completed state, failed state, and aborted state, age of the job, backlog, expired jobs, and we should definitely track availability metrics of the APIs and the number of read-driven tasks. The other discussion points could be around the scalability dimensions, like how the system would scale with respect to job and customers. I'll leave this as an exercise. And then in terms of monitoring, we already discussed about observability metrics. So it'll be good to think about like how or what kind of alarm thresholds we'll have for the various observability metrics. Here are some of the recommended readings on this subject. If you're short on time, I'll just recommend read the first one, that is asynchronous task scheduling at Dropbox. Others are optional. Hope this was useful. Do comment with your thoughts and suggestions. Bye for now.